Well, welcome back to our course, Computer Organization and Architecture. This lecture, we're going to get into instruction sets, characteristics, and functions. And so this is now getting into this fourth major section that we'll have in this course, and we'll get a chance to get exposed to instruction sets in assembly language. So we will get a chance to play with this in our course using a MIPS emulator. And so this will be something based on the ARM architecture. So let's just do a quick summary of what we're going to cover, then we'll get into it, and then we'll come back to this chart at the very end. So first of all, we'll get a chance to talk about machine instruction characteristics. We'll talk about the types of operands, and then we'll get into, as we've done in the past, reflect on both the x86 architecture from Intel and the ARM architecture. First of all, looking for the data types. We'll think about the types of operations, and then finally we'll talk about the operation types for the x86 as well as the ARM. So let's go and get started. So for the machine instruction set, the operation of the processor is determined by the instruction it executes, referred to as machine instructions or computer instructions. The collection of different instructions that the processor can execute is referred to as the processor's instruction set. Each instruction must contain information required by the processor for execution. So that's a little bit of a summary there. Now let's talk about the instruction cycle state diagram. Each instruction must contain the information required for the processor for execution. So in figure 13.1, which we're showing here, which repeats figure 3.6, it shows the steps involved in instruction execution and by implication defines the elements of machine instruction. These elements are as follows. First, the operation codes, it specifies the operation to be performed, for example, add or IO. The operation is specified by a binary code known as the operation code or opcode. There's a source operand reference. The operation may involve one or more source operands, that is, operands that are inputs from the operation. Results operand reference. The operation may produce a result. And then we have the next instruction reference. This tells the processor when to fetch the next instruction after the execution of the instruction is complete. So let's think about source and result operands and how they can fit into one of four areas. So first of all, for the main or virtual memory, as with the next instruction references, the main or virtual memory address must be supplied. For the processor registers, with rare exceptions, a processor contains one or more registers that may be referenced by machine instructions. If only one register exists, reference to it may be implicit. If more than one register exists, then each register is assigned a unique name or number, and the instruction must contain the number of the desired registers. For immediate, the value of the operand is contained in a field and the instructions being executed. And kind of going in a circle, here next, IO device, the instructions must specify the IO modules and device for the operation. If memory mapped IO is used, this is just another main or virtual memory address. So let's talk about a simple instruction format. With the computer, each instruction is represented by a sequence of bits. The instruction is divided into fields, the corresponding to the constituent elements of the instructions. A simple example of an instruction format is shown here in figure 13.2. As another example, the IAS instruction format is shown in figure 1.7, and so you might want to go back there and check that out. With most instruction sets, more than one format is used. During instruction execution, an instruction is read into an instruction register, IR, in the processor. the processor must be able to extract the data from the various instruction fields to perform the required operation. It is difficult for both the programmer and the reader of textbooks to deal with binary representation of machine instructions. And so you'll see that as you're reading the text, and hopefully we'll make it a little bit easier with these lectures. Thus, it has become common practice to use a symbolic representation of machine instructions. An example of this was used for the IAS instruction set in table 1.1. So you might want to go back and review that if you would like. Opcodes are represented by abbreviations called mnemonics that indicate the operation. Common examples are add for add, SUB, or sub for subtract, mul for multiply, div for divide, load for load data from memory, and store data to memory. So they try and be representative of the kind of things that they do, if at all possible. Operands are also represented symbolically. For example, the instruction add r comma y may mean add the value contained in data location y to the contents of register r. In this example, y refers to the address of a location in memory, and r refers to a particular register. Note that the operation is performed on the contents of a location, not an address. Thus, it is possible to write a machine language program in symbolic form. Each symbolic opcode has a fixed binary representation, and the programmer specifies the location of each symbolic operand. For example, the programmer might begin with a list of definitions: x equals 513, y equals 514, and so on. A simple program would accept this symbolic input, convert opcodes and operand references to binary format, and construct binary machine instructions. That's what the CPU is actually going to use for execution. Machine language programmers are rare to the point of non-existence. Most programmers today are written in high-level language, or failing that, assembly language, which is discussed in chapter 15, and we'll be coming back to that. However, symbolic machine language remains a useful tool for describing machine instructions, and we will use it for that purpose. A computer should have a set of instructions that allows a user to formulate any data processing task. Another way to view it is to consider the capabilities of high-level programming language. Any program written in a high-level language must be translated into machine language to be executed. Thus, the set of machine instructions must be sufficient to express any of the instructions from a high-level language. With this in mind, we can categorize instruction types as follows. For data processing, you can think of arithmetic and logic instructions. For data storage, the movement of data into or out of registers and or memory locations. For data movements, I/O instructions, and for control, test, and branch instructions. Arithmetic instructions provide computational capabilities for processing numeric logic. Logic, that is Boolean instructions, operate on the bits of a word as bits rather than as numbers. Thus, they provide capabilities for processing any other type of data the user may wish to employ. These operations are performed primarily on data in processor registers. Therefore, there must be memory instructions for moving data between memory and the registers. I/O instructions are needed to transfer programs and data into memory, and the results of computations back out to the user. Test instructions are used to test the value of a data word or the status of a computation. Branch instructions are then used to branch to a different set of instructions depending on the decision made. One of the traditional ways of describing processor architectures in terms of the number of addresses contained in each instruction. This dimension has become less significant with the increasing complexity of processor design. Nevertheless, it is useful at this point to draw and analyze this distinction. What is a maximum number of addresses one might need in an instruction? Evidently, arithmetic and logic instructions will require the most operands. Virtually all arithmetic and logic operations are either unary, that is one source operand, or binary, two source operands. Thus, we would need a maximum of 2 addresses to reference the source operand. The result of an operand must be stored, suggesting a third address which defines a destination operand. Finally, after completion of an instruction, the next instruction must be fetched and its address is needed. This line of reasoning suggests that an instruction could plausibly be required to contain 4 address references, 2 source operands, 1 destination operand, and the address of the next instruction. In most architectures, many instructions have 1, 2, or 3 operand addresses, and the operand of the next instruction being implicit, which is obtained from the program counter. Most architectures also have a few special purpose instructions with more operands. For example, the load and store multiple instructions of the ARM architecture described in chapter 14 designate up to 17 operands in a single instruction. Figure 13.3 that we're showing here compares typical 1, 2, and 3 address instructions that could be used to compute 1 equals the quantity A minus B divided by the quantity C plus the quantity D times E. With 3 addresses, each instruction specifies 2 source operand locations and a destination operand location. Because we choose not to alter the value of any of the operand locations, a temporary location T is used to store some intermediate results. Note that there are 4 instructions and that the original expression had 5 operands. 3 address instruction formats are not common because they require relatively long instruction format to hold the 3 address references. With 2 address instructions and for binary operations, 1 address must do double duty as both an operand and as a result. Thus, the instruction sub YB carries out the calculation Y minus B and then stores a result in Y. The 2 address format reduces the space requirement, but also introduces some awkwardness. To avoid altering the value of an operand, a move instruction is used to move one of the values to a result or temporary location before performing the operation. Our sample program expands to 6 instructions. Simpler yet is the 1 address instruction. For this to work, a second address must be implicit. This was common in early machines, with the implied address being a processor register known as the accumulator, AC. The accumulator contains one of the operands and is used to store the result. In our example, 8 instructions are needed to accomplish the task this way. It is in fact possible to make do with 0 addresses for some instructions. 0 address instructions are applicable to a special memory organization called a stack. A stack is a last in, first out set of locations. The stack is in a known location, and often at least the top 2 elements are in processor registers. Thus, 0 address instructions would reference the top 2 stack elements. Stacks are described in Appendix E. Their use is explored further later in this chapter and chapter 14. So in table 13.1, what we're showing here, it summarizes the interpretation to be placed on the instructions with 0, 1, 2, or 3 addresses. In each case in the table, it is assumed that the address of the next instruction is implicit and that 1 operation with 2 source operands and 1 result operand is to be performed. The number of addresses per instruction is a basic design decision. Fewer addresses per instruction results in instructions that are more primitive, requiring a less complex processor. It also results in instructions of shorter length. On the other hand, programs contain more total instruction, which in general result in longer execution time and longer, more complex programs. Also, there is an important threshold between 1 address and multiple address instructions. With 1 address instruction, the programmer generally has available only 1 general purpose register, the accumulator. With multiple address instruction, it is common to have multiple general purpose registers. This allows some operations to be performed solely on registers. Because register references are faster than memory references, this speeds up the execution. For reasons of flexibility and ability to use multiple registers, most contemporary machines employ a mixture of 2 and 3 address instructions. The design trade-offs involved in choosing the number of addresses per instructions are complicated by other factors. There is the issue of whether an address references a memory location or a register. Because there are fewer registers, fewer bits are needed for a register reference. Also, as we shall see in chapter 14, a machine may offer a variety of addressing modes, and the specification of mode takes 1 or more bits. The result is that most processor designs involve a variety of instruction formats. So one of the most interesting and most analyzed aspect of computer design is instruction set design. The design of an instruction set is very complex because it affects so many aspects of the computer system. The instructions set defines many of the functions performed by the processor and thus has a significant effect on the implementation of the processor. The instruction set is the programmer's means of controlling the processor. Thus, the programmer requirement must be considered in designing the instruction set. It may surprise you to know that some of the most fundamental issues relating to a design of instruction sets remain in dispute. Indeed, in recent years, the level of disagreement concerning these fundamentals have actually grown. The most important of these fundamental design issues include the following: operation repertoire, how many and what operations to provide and how complex the operation should be; data types, the various types of data upon which operations are performed; instruction format, instruction length and bit, number of addresses, size of the various fields, and so on; registers, and the number of processor registers that can be referenced by instructions and their use; and addressing, the number of modes by which the address of an operand is specified. These issues are highly interrelated and must be considered together in designing an instruction set. The textbook and the course must consider them in some sequence, but an attempt is made to show the interrelationship. Because of the importance of this topic, much of part 3 and the text and what we're covering in these lectures is devoted to instruction set design. Following this overview section, this chapter and this lecture examines data types and operation repertoire. Chapter 14 examines addressing modes, which includes a consideration of registers and instruction formats. Chapter 17 examines the reduced instruction set computer RISC. RISC architecture calls into question many of the instruction set design decisions traditionally made in commercial computers. So machine instructions operate on data. The most important general categories of data are addresses, numbers, characters, and logical data. We shall see in discussing address modes in chapter 14, the addresses are in fact a form of data. In many cases, some calculations must be performed on the operand reference in an instruction to determine the main or virtual memory address. In this context, addresses can be considered to be unsigned integers. Other common data types are numbers, characters, and logical data, and each of these is briefly examined in this section. Beyond that, some machines define specialized data types or data structures. For example, there may be machine operations that operate directly on a list or a string of characters. In terms of numbers, all machine languages include numeric data types. Even in non-numeric data processing, there is a need for numbers to act as counters, field widths, and so forth. An important distinction between numbers used in ordinary mathematics and numbers stored in a computer is that the latter are limited. This is true in two senses. First, there is a limit to the magnitude of numbers representable on a machine, and second, in the case of floating point numbers, a limit to their precision. Thus, the programmer is faced with understanding the consequences of rounding, overflow, and underflow. Three types of numeric data are common in computers. First, binary integers or binary fixed point, binary floating point, and decimal. We examine the first two in some detail in chapter 10, and it remains to say a few words about decimals here. Although all integer computers operations are binary in nature, the human users of the system deal with decimal numbers. Thus, there is a necessity to convert from decimal to binary on input and from binary to decimal on output for applications in which there is a great deal of I/O and comparatively little and comparatively simple computation is preferable to store and operate on the numbers in decimal format. The most common represented for this purpose is packed decimal. With packed decimal, each decimal digit is represented by a 4-bit code in this obvious way with 2 digits stored per bit. Thus 0 is 000, 1 is 0001, C 8 is 1000, and 9 is 1001. So those are just a couple examples of that. Note that this is rather inefficient code because only 10 of the 16 possible 4-bit values are used. To form numbers, a 4-bit code are strung together usually in multiples of 8 bits. Thus the code for 246 is 0000, 0010, 0100, 0110. This code is clearly less compact than a straight binary representation, but it avoids a conversion overhead. Negative numbers can be represented by including a 4-bit sign digit at either the left or right end of the string of packed decimal digits. Standard sign values are 1100 for positive and 1101 for negative. Many machines provide arithmetic instructions for performing operations directly on packed decimal digits. This algorithm, the algorithms are quite similar to those described in section 10.3, but must take into account the decimal carry operation. Now, for characters, a common form of data is text or character strings. While textual data are more convenient for human beings, they cannot in character form be easily stored or transmitted by data processing and communication systems. Such systems are designed for binary data. Thus, a number of codes have been devised by which characters are represented by a sequence of bits. Perhaps the earliest common example of this is the Morse code. Today, the most commonly used character reference is the International Reference Alphabet, referred to in the United States as the American Standard Code for Information Interchange, or ASCII. And you can look at Appendix D if you want to get more perspective on that. Each character in this code is represented by a unique 7-bit pattern. Thus, 128 different characters can be represented. This is a larger number than is necessary to represent printable characters, and some of the patterns represent control characters. Some of these control characters have to do with controlling the printing of characters on a page. Others are concerned with communication protocols. IRA or ASCII encoded characters are almost always stored and transmitted using 8 bits per character. The 8-bit may be set to 0 or used as a parity bit for error detection. In this latter case, the bit is set such that the total number of binary ones in each octet is always odd, so that would be an odd parity, or always even, an even parity. Note in table D.1 in Appendix D that for the IRA bit patterns, 011 XXXX, the digit 0 through 9 are represented by their binary equivalent 0000 through 1001 in the rightmost 4 bits. This is the same code as the packed decimal. This facilitates conversions between 7-bit IRA and 4-bit packed decimal representation. Another code used to encode characters is the extended binary coded decimal interchange code, EBCDIC. And so EBCDIC is used on IBM mainframes. It is an 8-bit code. As with IRA, EBCDIC is compatible with packed decimal. In this case, the EBCDIC, the code 110000 through 11111001 represent the digits 0 through 9. Then we have logical data. Normally, each word or other addressable unit, byte or half word or and so on, is treated as a single unit of data. It is sometimes useful, however, to consider an n-bit unit as consisting of n 1-bit items of data, each item having the value 0 or 1. When data are viewed this way, they are considered to be logical data. There are 2 advantages to the bit-oriented view. First, we may sometimes wish to store an array of Boolean or binary data items, in which each item can take on only the value 1, that is true, and 0, that is false. With logical data, memory can be used most efficiently for this storage. Second, there are occasions when we wish to manipulate the bits of data items. For example, if floating point operations are implemented in software, we need to be sure to shift significant bits in some operations. Another example, to convert from IRA to packed decimal, we need to extract the rightmost 4 bits of each byte. Note that in the preceding examples, the same data are treated sometimes as logical and other times as numerical or text. The type of a unit of data is determined by the operation being performed on. While this is not normally the case in high-level language, it is almost always the case with machine language. The x86 can deal with data types of 8, that's a byte, 16 word, or 32 double word, or 64 quad word, and 128 double quad word bits in length. To allow maximum flexibility in data structures and efficient memory utilization, words need not be aligned at even number addresses. Double words need not be aligned at address evenly divisible by 4, and quad words need not be aligned at addresses evenly divisible by 8, and so on. However, when data are accessed across a 32-bit bus, the data transfers take place in units of double words, beginning at addresses divisible by 4. The processor converts the request for misaligned values into a sequence of requests for the bus transfer. As with all of the Intel x86 machines, the x86 uses the little endian style, that is, the least significant byte is stored in the lowest address. You can see Appendix 13A for discussion on the endianness. The byte, word, double word, and quad word and double quad word are referred to in general data types. In addition, the x86 supports an impressive array of specific data types that are recognized and operates on particular instructions. Table 13.2 summarizes these types. And so that's what we're showing here as I went through that overview. Figure 13.4 that we're showing here illustrates the x86 numerical data types. The signed integer are in 2's complement representation and may be 16, 32, or 64 bits long. The floating point type actually refers to a set of types that are used by the floating point units and operated on by the floating point instruction. The 3 floating point representations conform to the IEEE 354 standard. The packed SIMD, single instruction multiple data types were introduced to the x86 architecture as part of the extensions of the instruction set to optimize performance of multimedia applications. These extensions include MMX, multimedia extension, and SSE, streaming SIMD extensions. The basic concept is that multiple operands are packed into a single reference memory item and that these multiple operands are operated on in parallel. The data types are as follows: packed byte and packed byte integer, packed bytes packed into 64-bit quad words or 128 double quad words interpreted as a bit field or as an integer. There's the packed word and packed word integer, 16-bit word packed into a 64-bit quad word or a 128-bit double quad word interpreted as a bit field or as an integer. Then there's the packed double word or packed double word integer, or a 32-bit double word packed into a 64-bit quad word or a 128 double quad word interpreted as a bit field or as an integer. There's the packed quad word and packed quad word integer, two 64-bit quad word packed into a 128-bit double quad word interpreted as a bit field or as an integer. And finally, the packed single precision floating point and packed double precision floating point, four 32-bit floating point or two 64 floating point values packed into a 128 double quad word. Okay, let's talk about the ARM data types. ARM processors support data types of 8, that is a byte, 16, a half word, and 32 word bits in length. Normally, half word access should be half word aligned and word access should be word aligned. For non-aligned access attempts, the architecture supports 3 alternatives. The default case, the address is treated as a truncated with address bits 1:0 treated as 0 for words accesses and addresses bit 0 treated as 0 for half word accesses. Load single word ARM instructions are architecturally defined to rotate right the word aligned data transferred by a non-word aligned address 1, 2, or 3 bytes, depending on the value of the 2 least significant address bits. There's for alignment checking, when the appropriate control bit is set, a data abort signal indicates an alignment fault for attempting unaligned access. For unaligned access, when this option is enabled, the processor uses one or more memory accesses to generate the required transfer of adjacent bytes transparently to the programmer. For all 3 data types, byte, half word, and word, an unsigned interpretation is supported in which the value represents an unsigned non-negative integer. All 3 data types can also be used for 2's complement signed integer. The majority of ARM processor implementations do not provide floating point hardware, which saves power and area. If floating point arithmetic is required in some processor, it must be implemented in software. ARM does not support an optional floating point coprocessor that supports the single and double precision floating point data defined in IEEE 754. So for an ARM Endian support, a state bit, E bit, in the system control register is set and cleared under program control using the set and instruction. The E bit defines which endian to load and store data. Figure 13.5 illustrates the functionality associated with the E bit for a word load or store operation. This mechanism enables an efficient dynamic data load and store for system designers who know they need to access data structures in the opposite endianness to their operating system or environment. Note that the address of each data byte is fixed in memory. However, the byte lane in a register is different. Okay, let's now talk about the common x86 instruction set operations. So the number of different opcodes varies widely from machine to machine. However, the same general types of operations are found on all machines. A useful and typical characterization is as follows: data transfer, arithmetic, logical, conversion, input-output, system control, and transfer control. Table 13.3 lists common instruction types in these categories. This section provides a brief summary of these various types of operations, together with a brief discussion of the action taken by the processor to execute a particular type of operation. Then this is summarized in table 13.4. The later topic is examined in more detail in chapter 16. Okay, so this is the second part of table 13.3. I won't go over this. You can pause this and look at it more carefully if you would like. And finally, this is the third part of table 13.3. Once again, you can pause this and look at this as long as you would like to get familiar with that. Table 13.4, which we had mentioned, this shows the processor actions for various types of operations. I'm not going to go through this in detail, but you can feel free to pause the video and once again go over that on your own. The most fundamental type of machine instructions in the data is the data transfer instruction. The data transfer instruction must specify several things. First, the location of the source and destination operands must be specified. Each location could be memory, a register, or a top of the stack. Second, the length of data to be transferred must be indicated. Third, as with all instructions with operands, the mode of addressing for each operand must be specified. This latter point is discussed in chapter 14. So the choice of data transfer instructions to include in an instruction set exemplifies the kind of trade-offs that the designer must make. For example, the general location, memory, or location of an operand can be indicated in either the specification of the opcode or the operand. Table 13.5 shows examples of the most common IBM EAS 390 data transfer instructions. Note that there are variants to indicate the amount of data to be transferred: 8, 16, 32, or 64 bits. Also, there are different instructions for register to register, register to memory, memory to register, and memory to memory transfers. In contrast, the VAX has a MOV instruction with variants for different amounts of data to be moved, but it specifies whether an operand is register or memory as part of the operand. The VAX approach is somewhat easier for the programmer who has fewer mnemonics to deal with. However, it is also somewhat less compact than the IBM EAS 390 approach because the location, the registers versus memory of each operand must be specified separately in the instruction. In terms of processor action, data transfer operations are perhaps the simplest type. If both source and destination are registers, then the processor simply causes data to be transferred from one register to another. This is an operation internal to the processor. If one or both operands are in memory, then the processor must perform some or all of the following actions. 1, calculate the memory address based on the address mode, which is discussed in chapter 14. 2, if the address refers to virtual memory, translate from virtual to real memory addresses. 3, determine whether the address item is in cache. And 4, if not, issue a command to the memory module. Well, let's talk about arithmetic. Most machines provide the basic arithmetic operations of addition, subtraction, multiplication, and division. These are invariably provided for signed integers, fixed point numbers. Often they are also provided for floating point and unpacked decimal numbers. Other possible operations include a variety of single operand instructions, for example, absolute, taking the absolute value of the number, negative, to negate the operand, increment, add one to the operand, and decrement, subtract one from the operand. The execution of the arithmetic instruction may involve data transfer operations to position operands for input to the ALU and to deliver the output of the ALU. Figure 3.5, you might want to go back and check that out, illustrates the movement involved in both data transfer and arithmetic operations. In addition, of course, the ALU portion of the processor performs the desired operation. Now, for basic logic operations, most machines also provide a variety of operations for manipulating individual bits of a word or other addressable unit, often referred to bit twiddling. They're based upon Boolean operations, which is something that we talked about in chapter 12. Some of the basic logical operations that can be performed on Boolean or binary data are shown in table 13.6, which we have up here now. The not operation inverts a bit, and or an exclusive or XOR are the most common logical functions with two operands equal. Two operands equal is a useful binary test as well. In addition to bitwise logical operation, most machines provide a variety of shifting and rotating functions. You can see table 13.3c for more details. The most basic operations are illustrated in figure 13.6, which we're showing here. With a logical shift, the bits of a word are shifted left or right. On one end, the bits shifted out is lost. On the other end, a 0 is shifted in. Logical shifts are usually primarily for isolating fields within a word. The zeros that are shifted into a word displace unwanted information that is shifted off the other end. Next, an example, suppose we wish to transfer characters of data to an I/O device, one character at a time. If each memory word is 16 bits in length, contains two characters, we must unpack the characters before they can be sent. To send the two characters in a word, load the word into a register. That's number one. Two, shift to the right 8 times. This shifts the remaining characters to the right half of the register. Perform I/O. That's number three, that the I/O module reads the lower 8 bits from the data bus. The preceding steps results in sending the left-hand character to send the right-hand character, number one, load the word again in the register, and with and number two, and A and D with 00000000 and 11111111. That's 8 zeros and 8 ones. This masks out the characters on the left. And number three, perform the I/O. The arithmetic shift operation treats the data as a signed integer and does not shift the signed bit. On a right arithmetic shift, the signed bit is replicated into the bit position to its right. On a left arithmetic shift, the logical left shift is performed on all the bits except the signed bits, which is retained. These operations can speed up certain arithmetic operations. With numbers in twos complement notation, a right arithmetic shift corresponds to a division by 2. That's a useful thing. A right arithmetic shift corresponds to a division by 2 with truncation for odd numbers. Both an arithmetic left shift and a logical left shift correspond to a multiplication by 2 when there is no overflow. If overflow occurs, arithmetic and logical left shift operations produce different results. But the arithmetic left shift retains a sign of the number. Because of the potential for overflow, many processors do not include this instruction, including PowerPC and Itanium. Others, such as the IBM EAS390, do offer the instruction. Curiously, the x86 architecture includes an arithmetic left shift, but defines it to be identical to a logical left shift. For rotate or cyclical shift, the operations preserve all of the bits being operated on. One use of the rotate is to bring each bit successfully into the leftmost bit, where it can be identified by testing the sign of the data, treated as, in other words, it's treated as a number. As with arithmetic operations, logical operations involve ALU activity and may involve data transfer operations. Table 13.7 that we're showing here gives examples of all of the shift and rotate operations discussed in this subsection. So conversion instructions are those that change the format or operates on the format of data. An example is converting from decimal to binary. An example of a more complex editing instruction is the EAS390 translate TR instruction. This instruction can be used to convert from an 8-bit code to another, and it takes 3 operands: TR, R1, open paren L, close parentheses L, comma R2. So just keep that in mind. The operand R2 contains the address of the start of a table of 8-bit codes. The L bytes starting at the address specified by R1 are translated, each byte being replaced by the content of the table entry indexed by that byte. For example, to translate from EBCDIC to IRA, we first create a 256 byte table in storage located, say, at 1000 to 10FF hexadecimal. The table contains the characters of the IRA code and the sequence of the binary representation of the EBCDIC code. That is, the IRA code is placed in the table at the relative location equal to the binary value of the EBCDIC code of the same character. Thus, locations 10F0 through 10F9 will contain the values 30 through 39 because F0 is an EBCDIC code for the digit 0, and 30 is the IRA code for the digit 0, and so on through digit 9. Now suppose we have the EBCDIC for the digits 1984 starting at location 2100, and we wish to translate to IRA. We can assume the following locations: 2100 to 2103 contains F1, F9, F8, and F4. R1 contains 2100, R2 contains 1000. Then if we execute TR R1, open parentheses 4, close parentheses 4, comma R2, trying to have you, if you want, you could write that down so you can see what I'm talking about. Locations 2100 to 2103 will contain 31, 39, 38, and 34. So a little bit more detail, you can also see the textbook for some of what I was just walking through. For input and output instructions, we know that input and output instructions were discussed in some detail in Chapter 8. As we saw, there are a variety of approaches taken, including isolated programmed I/O, memory map programmed I/O, direct memory access, and the use of an I/O processor. Many implementations provide only a few input-output instructions with the specific actions specified by parameters, codes, or command words. System control instructions are those that can be executed only while the processor is in a certain privileged state or is executing a program in a special privileged area of memory. Typically, these instructions are reserved for the use of the operating system. Some examples of system control operations are as follows. A system control instruction may read or alter a control register. We discussed control registers in chapter 16. So we'll be getting to that. Another example is an instruction to read or modify a storage protection key, such as used in the CS390 memory system. Another example is access to process control blocks in a multi-programming system. For transfer control, for all the operation types discussed so far, the next instruction to be performed is the one that immediately follows. In memory, the current instruction, however, a significant fraction of the instructions in any program have as their function changing the sequence of the instruction execution. For these instructions, the operation performed by the processor is to update the program counter to contain the address of some instruction in memory. There are a number of reasons why transfer of control operations are required. Among the most important are the following. In the practical use of computers, it is essential to be able to execute each instruction more than once and perhaps many thousands of times. It may require thousands or perhaps millions of instructions to implement an application. This would be unthinkable if each instruction had to be written out separately. If a table or a list of items is to be processed, a program loop is needed. One sequence of instructions is executed repeatedly to process all the data. Virtually all programs involve some decision making. We would like the computer to do one thing if one condition holds and another thing if another condition holds. For example, a sequence of instruction computes the square root of a number. At the start of the sequence, the sign of the number is tested. If the number is negative, the computation is not performed, but an error is reported. To compose correctly a large or even medium-sized computer program, it is an exceedingly difficult task. It helps if there are mechanisms for breaking the task up into smaller pieces that can be worked on one at a time. We now turn to a discussion on the most common transfer control operations found in instruction sets, that is branch, skip, and procedure call. A branch instruction, also called a jump instruction, has one of its operands, the address of the next instruction to be executed. Most often, the instruction is a condition branch instruction. That is, a branch is made, update the program counter to equal address specified in the operand, only if a certain condition is met. Otherwise, the next instruction is in sequence is executed. It is incremented program counter as usual. A branch instruction in which the branch is always taken as an unconditional branch. There are two common ways of generating the condition to be tested in a conditional branch instruction. First, most machines provide a 1-bit or multiple bit condition code that is set as a result of some operation. This code can be thought of as a short visual user visible register. As an example, an arithmetic operation, add, subtract, and so on, could set up a 2-bit conditional code, one with the following 4 values, 0, positive, negative, overflow. On such a machine, there could be 4 different conditional branch instructions. BPR X position to locate X if the result is positive. BRN X branch to location N if the result is negative. BRZ X branch to location X if the result is 0. BRO X branch to the location X if an overflow occurs. If all of these in all these cases, the result refers to the result of the most recent operation that set the condition code. Another approach that can be used with a 3 address instruction format is to perform a comparison and specify a branch in the same instruction. For example, BRE R1, R2, X branch to X if content of R1 is equal to the contents of R2. Figure 13.7 I'm showing here shows examples of these operations. Note that a branch can be either forward, that is an instruction with a higher address, or backwards, that is to a lower address. The example shows how an unconditional and a conditional branch can be used to create a repeating loop of instructions. The instruction in location 202 through 2010 will be executed repeatedly until the result of subtracting y from x is 0. Another form of transfer control instruction is a skip instruction. The skip instruction includes an implied address. Typically, the skip implies that one instruction be skipped, thus the implied address equals the address of the next instruction plus one instruction length. Because the skip instruction does not require a destination address field, it is free to do other things. A typical example is to increment and skip if 0, ISZ instruction. Now for procedure call instructions, perhaps the most important innovation in the development of programming language is the procedure. Procedure is a self-contained computer program that is incorporated into a larger program. At any point in the program, the procedure may be invoked or called. The processor is instructed to go and execute the entire procedure and then return to the point from which the call took place. The two principal reasons for the use of procedure are economy and modularity. A procedure allows the same piece of code to be used many times. This is important for economy and programming effort and for making the most efficient use of storage space in the system. The program must be stored. That is, the program must be stored. Procedures are also large programming tasks to be subdivided into smaller tasks. This use of modularity greatly eases the programming task. The procedure mechanism involves two basic instructions: a call instruction that branches from the present location to the procedure, and a return instruction that returns from the procedure to the place from which it was called. Both of these are forms of branching instructions. Here in figure 13.8, we have 13.8a illustrates the use of procedure to construct a program. In this example, there is a main program starting at location 4000. The program includes a call to procedure proc1 starting at location 4500. When this call instruction is encountered, the processor suspends the execution of the main program and begins the execution of proc1 by fetching the next instruction from the location of 4500. With proc1, there are two calls to proc2 at location 4800. In each case, the execution of proc1 is suspended and proc2 is executed. The return statement causes the processor to go back to the calling program and continue execution at the instruction after the corresponding call instruction. The behavior is illustrated in figure 13.8b. 3 points are worth noting. 1, a procedure can be called from more than one location. 2, a procedure call can appear in a procedure. This allows the nesting of procedures to any arbitrary depth. And 3, each procedure call is matched by a return in the call program. Because we would like to be able to call a procedure from a variety of points, a processor must somehow save the return address so that the return can take place appropriately. There are 3 common places for storing the return address: a register, the start of a called procedure, or the top of the stack. A re-entrant procedure is one in which it is possible to have several calls open to it at the same time. A recursive procedure, that is one that calls itself, is an example of the use of this feature. You can see Appendix F for more details. If parameters are passed via registers or memory for a re-entrant procedure, some code must be responsible for saving the parameters so that the registers or memory space are available for other procedure calls. A more general and powerful approach is to use a stack. You can see Appendix A for discussion of stacks. When the processor executes a call that places the return address on the stack, When it executes a return, it uses the address on the stack. Figure 13.9 that we're showing here illustrates the use of the stack. In addition to providing a return address, it is also often necessary to pass parameters with a procedure call. These can be passed in registers. Another possibility is to store the parameters in memory just after the call instruction. In this case, the return must be to the location following the parameters. Again, both of these approaches have drawbacks. If registers are used, the call program and the calling program must be written to assure that the registers are used properly. The storing of parameters in memory makes it difficult to exchange a variable number of parameters. Both approaches prevent the use of re-entrant procedures. A more flexible approach to parameter passing is a stack. When the processor executes a call, it not only stacks the return address, it stacks parameters to be passed to the call procedure. The called procedure can access the parameters from the stack. Upon return parameters can also be placed on the stack. The entire set of parameters, including return address, that is stored for a procedure invocation is referred to as a stack frame. An example is provided in figure 13.10, which we're showing here. The example refers to a procedure P in which the local variable x1 and x2 are declared, and procedure Q, which P can call, and in which the local variable y1 and y2 are declared. In this figure, the return point for each procedure is the first item stored in the corresponding stack frame. Next is stored a pointer to the beginning of the previous frame. This is needed if the number of length or parameters to be stacked is variable. The x86 provides a complex array of operation types, including a number of specialized instructions. The intent was to provide tools for the compiler writer to produce optimized machine language translation of high-level language programs. Most of these are the conventional instructions found in most machine instruction sets, but several types of instructions are tailored to the x86 architecture are of particular interest. You can see Appendix A. Well, there's external things that the textbook refers to for possible ways that you can look at that for list of the x86 instructions together with the operands for each and the effects of the instructions on the condition codes. And so just continue on, there's other references as well. The x86 provides 4 instructions to support procedure calls and returns: call, enter, leave, and return. It would be instructive to look at the support provided by these instructions. Recall from figure 13.10 that a common means of implementing the procedure call return mechanism is via the use of stack frames. When a new procedure is called, the following must be performed upon entry to a new procedure: push the return point on the stack, push the current frame point on the stack, copy the stack pointer as the new value of the frame pointer, and adjust the stack pointer to allocate a frame. The call instruction pushes the current instruction pointer value on the stack and causes jump to the entry point of the procedure by placing the address of the entry point in the instruction pointer. In the 8080 and 8086 machines, a typical procedure began with the steps push EBP, move EBP, comma ESP, sub ESP, comma space for the locals. And when ESP is the frame pointer and ESP is the stack pointer. In 8286 and later machines, the enter instruction performed all of the aforementioned operations in a single instruction. The enter instruction was added to the instruction set to provide direct support for the compiler. The instruction also includes a feature for support of what are called nested procedures. in languages such as Pascal, COBOL, and Ada, but not found in C or Fortran. It turns out that there are better ways of handling nested procedure calls for these languages. Furthermore, although the enter instruction saves a few bytes of memory compared with the push, move, and subsequence, it actually takes longer to execute. Thus, although it may have seemed a good idea to the instruction set designers to add this feature, it complicates the implementation of the processor while providing little or no benefit. We will see that in contrast, a RISC approach to procedure design would avoid complex instructions such as enter and might produce a more efficient implementation with a sequence of simpler instructions. Another set of specialized instructions deals with memory segmentation. These are privileged instructions that can only be executed from the operating system. They allow local and global segment tables, called descriptor tables, to be loaded and read, and for the privilege level of a segment to be checked and altered. The special instructions for dealing with the on-chip cache were discussed in Chapter 5 if you want to go back and review that. Status flags are bits and special registers that may be set by certain operations and used in conditional branch instructions. The term conditional code refers to the settings of one or more of the status flags. In x86 and many other architectures, status flags are set by arithmetic and compare operations. The compare operations in most languages subtracts two operands, as does a subtract operation. The difference is that a compare operation only sets status flags, whereas a subtract operation also stores the result of the subtraction in the destination operand. Some architectures also set status flags for data transfer instructions. Table 13.8 lists the status flags used on the x86. Each flag or combination of these flags can be tested for a conditional jump. Table 13.9 shows the condition codes combination, that is the combination of status flag values for which conditional jump opcodes have been defined. Several interesting observations can be made about this list. First, we may wish to test two operands to determine if one number is bigger than the other, but this will depend on whether the numbers are signed or unsigned. So you could keep that in mind. For example, the 8-bit number 8 ones, 1111, 1111 is bigger than 00000000 if the two numbers are interpreted as unsigned integers, but is less if they are considered as 8-bit 2's complement numbers. Many assembly languages therefore introduce the sets of terms to distinguish the two cases. If we are comparing two numbers as unsigned integers, we use the term less than or greater than. If we are comparing them as unsigned integers, we use the term below and above. The second observation concerns the complexity of comparing signed integers. A signed result is greater than or equal to 0 if 1, the signed bit is 0 and there is no overflow, or 2, the signed bit is 1 and there is an overflow. A study of figure 11.4 should convince you that the conditions tested for the various signed operations are appropriate. So you might want to go back to that chapter and look that up. In 1996, the introduction of the MMX technology into the Pentium product line, MMX is a set of highly optimized instructions for multimedia tasks. There are 57 new instructions that treat data in SIMD, single instruction multiple data fashion, which makes it possible to perform the same operations such as addition or multiplication on multiple data elements at once. Each instruction typically takes a single clock cycle to execute. For the proper application, these fast parallel operations yield a speed up of 2 to 8 times over comparable algorithms that do not use the MMX instructions. With the introduce of 64-bit x86 architectures, Intel has expanded this extension to include double quad word, that is 128-bit operands, and floating point operations. In this subsection, in the text and what we're talking about here, we describe the MMX features. The focus of the MMX is multimedia programming. Video and audio data are typically composed of large arrays of small data types, such as 8 or 16 bits, whereas conventional instructions are tailored to operate on 32 or 64-bit data. Here are some examples. In graphics and video, a single scene consists of an array of pixels, and there are 8 bits for each pixel, or 8 bits for each pixel color component: red, green, and blue. Typical audio samples are quantized using 16 bits. For some 3D graphic algorithms, 32 bits are common for basic data types. To provide for parallel operations on these data lengths, 3 new data types are defined in MMX. Each data type is 64 bits in length and consists of multiple smaller data fields, each of which holds a fixed point integer. The types are as follows: packed byte, 8 bytes packed into one 64-bit quantity; packed word, 4 16-bit words packed into 64 bits; and packed double word, 2 32-bit double words packed into 64 bits. Table 13.10 lists the MMX instruction set. Most of the instructions involve parallel operations on bytes, words, or double words. For example, the PSLLW instruction performs a left logical shift separately on each of the 4 words in the packed word operand. The pad B instruction takes the packed byte operation as an input and performs parallel additions on each byte position independently to produce a packed byte output. One unusual feature of the new instruction set is the introduction of the saturation arithmetic for byte and 16-bit word operands. With ordinary unsigned arithmetic, where an operation overflow, that is a carry out of the most significant bit, the extra bit is truncated. This is referred to as a wraparound because the effect of the truncation can be, for example, to produce an addition result that is smaller than the 2 operands. So figure 1311 shows a sequence of steps required for one set of pixels. The 8-bit conversion components are converted to 16-bit elements to accommodate the MMX 16-bit multiply capability. If these images are 640 by 480 resolution, and the dissolve technique uses all 256 possible values of the fadeaway, then the total number of instructions executed using MMX is 535 million. The same calculations performed without an MMX instruction requires 1.4 billion instruction executions. The ARM architecture provides a large collection of operation types. The following are the principal categories: load and store instructions. In the ARM architecture, only load and store instructions access memory locations. Arithmetic and arithmetic instructions are performed only on registers and immediate values encoded in the instructions. Limitation is characteristic of RISC design and is explored further in Chapter 17. The ARM architecture supports 2 broad types of instructions: the load or store the value of a single register, or a pair of registers from or to memory. 1, load or store a 32-bit word or a 8-bit unsigned integer, and 2, load or store a 16-bit unsigned half word and load and sign extend a 16-bit half word or an 8-bit byte. Branch instructions. ARM supports a branch instruction that allows a conditional branch forward or backward up to 32 megabytes. A subroutine called can be performed by a variant of the standard branch instruction, as well as allowing a branch forward or backward up to 32 megabytes. The branch with link BL instruction preserves the address of the instruction after the branch, that is the return address. In the LR, that is R14, branches are determined by a 4-bit condition field in the instruction. For data processing instruction, this category includes instructions, the logical instructions and or XOR, add and subtract instructions, and test and compare instructions. The multiply instructions, the integer multiply instructions operate on word or half-word operands and can produce normal or long results. For example, there is a multiply instruction that takes two 32-bit operands and produces a 64-bit result. Parallel addition and subtraction instructions. In addition to the normal data processing and multiply instructions, there are a set of parallel addition and subtraction instructions in which portions of two operands are operated on in parallel. For example, add 16 adds the top half words of two registers to form the top half word of the result, and adds the bottom half words of the same two registers to form the bottom half words of the result. These instructions are useful in image processing applications similar to the x86 MMX instruction. Then there's the extend instruction. These are several instructions for unpacking data by sign or zero, extending bytes to half words or words, and half words to words. And finally, there are status register access instructions. ARM provides the ability to read and also to write portions of the status register. The ARM architecture defines 4 conditional flags that are stored in the program status register: N, Z, C, and V. That is the negative, zero, carry, and overflow, with meanings essentially the same as the S, Z, C, and V flags in the x86 architecture. These 4 flags constitute a condition code in ARM. Table 1311 that we're showing here shows the combination of the condition for which conditional execution is defined. There are 2 unusual aspects to the use of the conditional codes in ARM. All instructions do not branch instructions. All instructions, not just branch instructions, include a conditional code field, which means that virtually all instructions may be conditionally executed. Any combination of flag setting except 1110 or 1111 in an instruction's conditional code field signifies that the instruction will be executed only if the condition is met. All data processing instructions, that is arithmetic and logical, include an S bit that signifies whether the instruction updates the condition flags. The use of conditional execution and conditional setting of the condition flags helps in the design of shorter programs that use less memory. On the other hand, all the instructions include 4 bits for the condition code, so there is a trade-off in the fewer bits in the 32-bit instructions are available for opcodes and operands. Because the ARM is a RISC design that relies heavily on registers addressing, this seems to be a reasonable trade-off. All right, well, that finishes what we are covering for this chapter. We talked about machine instruction characteristics, the various elements, representations, and how we go about thinking about how we're going to formulate the instruction sets. We talked about the type of operands with the number characteristics and the logical data. We then looked at the data types that are used in the Intel 86 and ARM ways of doing things, those architecture. We talked about the type of operations, data transfer, arithmetic, operation, conversion, input and output, system control, and transfer of control. And finally, we talked about the Intel x86 and the ARM operation types. All right, well, thank you very much. That'll end it for this lecture.